All together now, experiments with twisted 2D materials catch electrons behaving collectively. So, what are 2D materials? 2D materials are sheets of paper that are a single layer of atoms thick. Research led by a team of UW scientists and recently published in the journal Nature Physics reported that carefully constructed stacks of graphene can exhibit highly correlated electron properties. This likely relates to the emergence of exotic magnetic states. We've created an experimental setup that allows us to manipulate electrons in the graphene layers in a number of new, exciting ways, said co-senior author Matthew Yankowitz. Yankowitz is an assistant professor of physics at UW. He led the team along with Professor Xiaodong Zhu, another UW professor of physics. Since 2D materials are one layer of atoms thick, bonds between atoms only form in 2 dimensions, and particles, like electrons, can only move like pieces on a board game, side to side, front to back, or diagonally, but not up and down. These restrictions can imbue 2D materials with properties that their 3D counterparts lack, and scientists have been probing 2D sheets of different materials to characterize and understand these potentially useful qualities. The UW team worked with building blocks of bilayer graphene, 2 sheets of graphene layered naturally together. They stacked one bilayer on top of another for a total of 4 graphene layers and twisted them so that the layout of carbon atoms between the 2 bilayers were slightly out of alignment. In these instances, it no longer makes sense to describe what an individual electron is doing, but what all electrons are doing at once, said Yankowitz. It's like having a room full of people in which a change in any one person's behavior will cause everyone else to react similarly, said lead author Minhao He, a UW doctoral student in physics. They found that these states appeared to be driven by a quantum mechanical property of electrons called spin, a type of angular momentum. In regions near the correlated insulating states, they found evidence that all the electron spins spontaneously align. Much of what we're doing in this line of research is to try to create, understand, and control emerging electronic states, which can be either correlated or topological or possess both properties, said Zhu. There could be a lot we can do with these states down the road, a form of quantum computing, a new energy harvesting device, or some new types of sensors, for example. And frankly, we won't know until we try.